All right, we're doing describing motion and graphing motion part 2. These are the recorded notes for physics class. So we're still talking about the graphs. Let me move this, part 2. So a little bit of quick review. The slope of a position versus time graph is, and of course I moved that right over it, velocity. And then when we talk about the slope of part 1 right here, remember slope is y2 minus y1 over x2 minus x1. So we would have the change in x over the change in y, or I said that backwards, the change in y over the change in x. So 400 divided by 200 would give me a positive 2 meters per second. So this would be you going forward at a constant speed. And then the slope of part 2, well, it's a horizontally flat line. So that is 0. So we are stopped. Poor guy got a flat tire or something. Okay. And then the slope of 3 is going to be that we do the change in y divided by the change in x, which is going to be a negative value. It's a negative slope. And that means they've turned around and are heading back to their original position, but they are changing directions. And that's why it's going back to the origin. And the slope of this line is constant. So they are on cruise control while they're doing it. Okay, so consider a car that's moving with a constant rightward velocity of a positive 10 meters per second. Okay, so what does the velocity versus time graph of this look like? Well, it's going constant, meaning I've set the cruise control, so I'm not accelerating. So this would be a sloped line on a distance versus time graph. Well, on a velocity versus time graph, it's going to be a zero sloped line because the velocity is staying the same. So it is zero acceleration. Zero acceleration. So now if I have a car that's moving with rightward changing velocity, that is a car that's moving rightward and speeding up or accelerating, that on a position versus time graph, remember, was a curve. But on a velocity versus time graph, that looks like this. Okay, so it's a positively sloped line. This would have a positive slope. So it is, when it's in a positive direction, it's going to be in quadrant 1. So that's what I'm showing right here. And when it's speeding up, it's going to be a positive acceleration. Positive acceleration. So the slope of a velocity versus time graph is acceleration. So our units for the change in y over the change in x would be the change in velocity divided by the change in time. So velocity is going to be in meters per second, and time is going to be in seconds. So our units are going to be in meters per second squared or meters per second per second. I like meters per second squared better. Okay. Now, the instantaneous velocity of an object at a certain time is the slope of the velocity versus time graph at that time. It can be positive, it can be negative, or it can be zero. And really, the slope of, if it was instantaneous acceleration, it's just going to be that single point divided by, just like we had instantaneous speed on our other position versus time graph. This is a really good graph. The reason this is a really good graph is because it does have a title. It's got a good scale. It's got my variable and its units labeled on both sides. It's got my plotted points, and it's got a best fit line, actually. Excellent graph. Okay, so I'm actually going to talk about this graph in class, so I don't want to talk about it too much here. But positive slope in the positive quadrant means that I'm going in a positive direction and I'm speeding up. This one, I have a negative slope, but in a positive quadrant, so I'm in quadrant 1. So this actually means I'm going in a positive direction, but slowing down. And really, those are the only two we're going to talk about. I'm not even going to talk about these other ones. The only one I would like to talk about is this. This one is slowing down, and then it's changing directions and speeding up. So we'll talk about that in class. Okay. So this one right here, I could find the slope of this graph and find it is accelerating and it's going forward. It's still from 1 to 4 accelerating and going forward. And then from 4 to 9, it's still going forward, but now it's slowing down. At 9, it comes to a stop, and because it switches from quadrant 1 to quadrant 4, it changes directions. Now it's going away from the x-axis, so that means it's speeding up. So right here, oh, I cannot get my little squares in the right position today. Okay, so from 0 to 1, it's a positive 40 meters per second. So it's accelerating, and we're talking about upwards as being forward. And then from 1 to 4, it's still accelerating and it's still going upwards. From 4 to 9, it is decelerating or slowing down, and it's still moving upwards though because it's in quadrant 1. And then from 9 to 12, it is actually accelerating, but it's going down because it is getting larger in its negative velocities. Okay, we'll talk about the negative velocity in a little bit. Okay, in class. Right there, it is at rest and is switching directions. This is the graph of the moving dot. So it's accelerating up, accelerating up, accelerating up, decelerating up, and turning around and accelerating. So what is the acceleration of interval A? Well, interval A is right there. Okay. And interval A, the acceleration would be the change in y over the change in x. So that would actually be a plus 2 meters per second squared. What distance does it travel? Distance, how could I tell that from this graph? Well, believe it or not, the distance covered is the area under the line. Well, in the first 20 seconds, the area under the line is a triangle. The way to find the area of a triangle is 1/2 base times height. So 1/2 base times height would tell me it's 1/2 times 20 seconds times 40 meters per second, which would then give me 400 meters. So I could say that it traveled 400 meters in the first 20 seconds. Now I want to find the acceleration in B. Well, the acceleration in part B is a horizontally flat line. The slope of a horizontally flat line is going to be 0. So since it's going at constant velocity, then the acceleration is 0. Then what's the distance traveled from 20 to 40? Well, again, we look at it as the area under the curve or under the line. But the area under the line here is a square. So since that's going to be, area is going to be base times height, the base is 20 seconds, the height is 40 meters per second, so it's now gone 800 meters. So if I wanted to say how far has it gone from 0 to 40, I'd have to take 800 and add 400 meters to it, and that would be 1,200 meters. So it's gone 1,200 meters total. So distance under the line, or excuse me, area under the line on a velocity versus time graph is distance. We'll put that in our notes. That's the end. I'll see you in class. Have a great day.